Okay, our next speaker before the break is Oberhauser from the University of Oxford. So please.
Yeah, so thanks a lot for the invitation to this workshop. I was a bit in the same situation as Shume, so looked at what I've done in the past and then looked at the best fit of what you could call an anomalous diffusion. And I'm talking about the paper that appears last year in NeurIPS, which is sort of this machine learning conference. And essentially it's about diffusions on graphs, which explains the first part of the title. And the second part is sort of a very, very classic idea in stochastic analysis that you all know sort of the connection between, Brownian motion and the heat equation. That there is a very old idea that's saying instead of looking at the simple Markov process, I think about Brownian motion expanded with some other things, which gives me a much richer perspective, and sort of my old heat equation with the whole diffusion stuff appears sort of as the first coordinate of this whole story. But anyway, we'll come to this. The most important thing is probably that this is joint work with my PhD student, Chabatot, who's just about to finish, Derek Lee, who was my postdoc and just studied in Edinburgh, a tenure track position, and Celia Hacker, who was at the time we did this at, I think actually EPFL, and is now at the Max Planck Institute in Germany. Good, so what's the object that we care about? Well, that's a labeled graph. So I have a set of vertices, V. I have a subset of, all possible edges there, and then by a labeled graph, I mean there is a function. When I sort of plug in a vertex, it spits out a vector. Yeah, think about, simplest example, colors. Yeah, so associate with each vertex a color code or so. And the reason we care about this, or many people care about this, is because a lot of the data out in the world is of this graph form. Yeah. So classic benchmarks when you go in sort of machine learning things is, for example, I give you, chemists, they give you sort of some structure, molecular structure, and then what you want to decide without sort of doing experiments, is this a toxic compound or is it, not a toxic compound? Or things like citation networks, right? So just people connected who interact with each other. Is this a connection of, I don't know, mathematicians who discuss something, or is this, I don't know, terrorist network or whatever? Yeah, so many examples where sort of what you're after is give me a nice structured description of the graph, which I can plug into one of these, many machine learning classification tools, or other tasks like I only give you parts of the labels and you want to augment them and so on. Good. And sort of when you go sort of in this direction of data science, the first thing that you sort of look for is what you would call a feature map. Yeah? Or maybe if you come from statistics, you would call this a covariate function. Yeah? So where we plug in a graph, and so we are after this function psi. And what we do is really we think about this space of graphs as sort of this really non-Euclidean domain, right? There's no natural addition or structure on the set of graphs, and what we want to do is we want to sort of pull this through a map into a nice vector space, and then all the questions we have our original data in this original space, we actually just formulate them in this codomain after we pushed it through this feature map. Yeah? So the question really is, what makes a good feature map? Yeah? And then sort of you go through some wish list of very natural things you should ask for, and the first thing is something like clearly it should be in check. Yeah, so you should not lose information. In the setting of graphs, if you give me the graph in some adjacency matrix, then of course up to permutation of the nodes, this describes the same object. There's this notion of universality that if you want to learn a function like this classification of a graph, the idea is that it gets simpler in feature space, namely after you are in feature space, this just boils down to learning some linear functional in this feature space, which you then can learn with linear regression or more sophisticated things. There's this notion of characteristicness, which means if you have put a probability measure on the domain, so if you speak about random graphs and you take the expectation of your feature map, this thing should characterize the probability measure. Yeah? So think about classic case where you have vectors and you push them through the moment map where you have all the moments and you take the expectation, then you have the moment sequence, and this gives you a nice description of the underlying measure. Good, so that's what we are after, and then when you sort of start thinking about looking at the literature, well, graphs have been studied by a lot of people, and especially sort of in this computer science, machine learning community. So classic things they did was they sort of give you structured descriptions of a graph by sort of looking at subpatterns that emerge there, or exploring the graph with random walks, which is the direction we are going. Yeah, and here just for reference, some super classic papers. Things that really made the impact was this 2014 DeepWalk paper, and then it's still a very active community of people who do things. Good, so let's start with something super simple, which is just introducing some notation, random walk. Oops, sorry, do I go back? Random walk on a graph. Yeah, so I have n vertices. I have some subset of this. I have my edges, and then I have some labeling function. And then the first thing you do is you define this adjacency matrix, which is just 0 or 1, and the igest entry is, well, is the edge between node I and j, then it's 1, and otherwise it's 0. And then you define sort of classic random walk on this graph by saying if I'm in node I, in the next state I jump to node j, by just looking at how many outgoing edges are there, and then I uniformly at random choose one of them. Good, and then actually this random walk B is not what we care about. We care about looking at this random walk through our label function, right? So if this, think back about this example of a graph which has colors on its vertices, then what you see is sort of a random sequence of colors. Good, so we have this original random walk on the vertices, the random walk L lifted through our label map, and then a very natural object you run into is sort of this graph Laplacian. Yeah, and then first, one of the first exercises in your undergraduate Markov chain course is probably something like this, that you say, you start here with a vector where you plug in all the labels of your n many vertices, and then sort of it boils down to linear algebra to solve sort of like what the expected value after k steps of this random walk is, right? And the only thing that I would want to emphasize here is this is sort of like the nice differential equation here, but what matters a lot for where we're going is that this boils down to just plain linear algebra. You never solve this equation, you just take this transition matrix to the power k and multiply this with your starting position. So super trivial, or elementary. And now when you think about what this actually does is you say, well, really what I want to do is, what's the description of my graph from this perspective of, I have my labels, I diffuse them, and, for each node or each vertex, what's my description of what's going on in the neighborhood? Well, I just start my diffusion, and that's sort of my description of the local neighborhood structure. Right? So this is the idea of all these sort of computer science papers. They just send out your random walkers. After k steps, you call them and say, what do you see now? And then they say, well, I see, in this color example, I see a lot of red, I see a lot of blue, whatever. Then you average this out, and this sort of gives you a bit of a description of what the neighborhood, the local neighborhood of a given vertex looks like. Yeah? And this works, yeah, you sort of can turn this into a nice feature map. But clearly what is a problem here is that you lose a lot of information. Yeah? So the idea of this talk is to say, instead of just sending out your random walkers on the graph, and after k steps you call them and ask them what you see, instead you call them and you ask each of these guys, what did you see along your trajectory? Yeah? And they should tell you something like, well, first I saw a lot of red, then a lot of blue, a lot of green, this kind of stuff. Yeah? And this gives you a much better local description of what's going on. So somehow we care about not just the end state, but sort of the whole random walk history and sort of thing. Good, and this is then sort of where you can start doing a bit of maths. So this is sort of just the stuff that I just discussed. You have your uniform random walk on a graph. You look at the expected value after k steps. You have this classic diffusion equation. And this is sort of like the discrete time, discrete space object. And then, of course, sort of the underlying object here in continuous time, continuous space is classic heat equation with Brownian motion, right? So you have your Brownian motion, you have the Laplacian, and you have your heat equation, and which describes this expected value after time t. Good, and motivated by this, you go back sort of in very classic stochastic literature, and they tell you, okay, this is a nice story, but actually there is another object which is much richer than just the original Brownian motion, which is the so-called lifted Brownian motion. Yeah, so the object is the following. So I underlined here to make it different to this one. It's why we just put a 1 here for certain algebraic reasons. The second entry here is a vector, and the vector is just, you know, the integral. So this is just bt minus b0. Like as before, you have the same information at time t. But then when it gets interesting is sort of these higher order levels because you have these iterated integrals. Yeah? So here the next entry would be dB tensor 2. Yeah? So it's an element of RD to the tensor 2. But the ijth entry is exactly the integral of dBi against dBj over the simplex. Yeah? And I think I'm at least the third person who talks about the signature here. Yeah? Another name for this object here is the signature of Brownian motion. So Terry was here, gave a talk, I think Nihao as well. And the idea is that, well, you have the old information, right, of what you're doing at time t, but these higher order iterated integrals, they give you some information about what you did up to time t. So for example, the second entry here, which would be this d times d matrix, this 2 tensor, if you look at the asymmetric part of this tensor, it would be exactly the stochastic area. Yeah? The area that was spanned out by this two-dimensional path, and so on. And you can actually prove, if you go with m to infinity, this gives you a full description of a full characterization of this trajectory. Good, okay, and classic story going at least back to, I don't know, 1970s or so, of Malevin, Gavot, and many people. They said, okay, I studied this now as my underlying stochastic process. And again, I look now at the function of this process, at the expected value. And it turns out that this thing, as Prof here, satisfies PDE. And instead of the old Laplacian in RD, you have sort of this hypo-elliptic Laplacian. Yeah? So this is a very, very classic story in stochastic analysis. And the idea is that many things get easier and you see more by studying this richer diffusion model than the original one. Yeah? Good, and then obvious question is, here we have sort of the thing on the graph of this nice well-studied thing. We have this nice well-studied thing here. Okay, what's the analogous diffusion on a graph? Yeah? And that's essentially the whole idea of this, this talk, to fill this out and actually also fill it out in such a way that it's computable and you can do experiments this. Good. I skip this for now. And I continue here. Okay, so the idea is that we have our labeled graph, we have our random walk, you know, we look at the random walk in label space. And then what we do is, previously we just looked at the last step at time k. And now we take the whole sequence and we turn it into these iterated integrals, yeah? And although it's discrete time, what you can always do is take piecewise linear interpolation, calculate these iterated integrals, and the whole point of the previous slide, which I'm skipping because it's a bit more technical, is that this is sort of fairly easy to compute, yeah? It boils down to some sort of multiplication of tensors, yeah? And that's really the main idea, yeah? So that instead of just looking at the expected value of what happens at time k, we turn this into a signature. We look at the path signature of this whole random walk up to time k. And this is the object that will give us a much richer description of what is the neighborhood of node I, yeah? Because it incorporates everything my random walker has seen as it went along, you know, its exploration. Yeah? And maybe a good intuition for what these iterated integrals do. Sort of like if you do what I just said, you sort of spell this out in discrete time, and all these integrals they turn into iterated sums. You look at the coordinates of this. For example, in this case of random walk on a graph where it's labeled with colors, the second thing would exactly tell you information like how often did I see green before I saw blue, or so, yeah? Or how often did I see red before I saw, all sort of this information about two tuples. If you go to the third level, you see exactly, how often did I see, green before blue before red, yeah, and so on. So you see that there is also some good intuition in all this. Good. Okay, so now we sort of looked what people are doing. We sort of thought about this more from this diffusion perspective. Then we had the idea that you say, okay, this is just looking at the endpoint, but what we want to have is also the whole trajectory. And sort of from the math side, it's kind of clear what we want to do, but of course, a big issue when you talk about graphs and machine learning is the dimensionality of this problem. Yeah, so these graphs that you have in these benchmarks, they are massive. Yeah, they are sort of 10,000s of nodes or 100,000s. Think about social networks, stuff like this. Good. And another thing is, of course, this is not my description of what happens. What does the neighborhood of node I look like? And I said, well, the way we do it is we calculate these tensors up to, a tensor of degree m. RD to the tensor m, that's a lot of data. That scales like d to the power m. So at one point you really have also to sort of think about things like storage and stuff like this. Good. Anyway, back to business. We are still in the process of filling out this picture here, right? So this was the classic random walk on a graph, and now I want sort of this hypo-elliptic random walk on a graph and derive some equations where I can just do linear algebra. Okay, so classic story is for graphs, you care about the adjacency matrix. You have n vertices, and then basic observation, the ijth entry of this thing to the power k. This counts exactly the number of paths that connect vertex I with vertex j. Every undergraduate in maths has done this at one point. Yeah? Good. And now the main observation is, okay, what we care about here is this adjacency, this ring of matrices, of adjacency things. This is just a matrix ring. And, you can build a matrix ring over every other ring. So in particular, we can consider the matrix ring where the entries are elements of this tensor series. Yeah? So recall the signature of a path. It lives sort of in this RD, comma, RD tensor 2, RD dot 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 tensor M, yeah? This thing itself forms even more than a ring, it's an algebra. So what we can do is we can sort of lift our old adjacency matrix to a new adjacency matrix where the entries are now valued in H. So I didn't introduce this notation, but H is exactly the state space of this guy here, yeah? So it's exactly RD, RD tensor 2 up to RD tensor M. Good. Okay, so what we do is we lift somehow our old adjacency matrix to a matrix where the entries are now valued in this tensor algebra. And then the observation is if you multiply this with the same rules of classic matrix multiplication, yeah?
Yeah, but if you do this, then your filtration will be Brownian one. And the result states that most Brownian filtration is not.
Which filtration? Sorry?
There is some proved result that filtration generated by most Brownian motion with more than 3 vertices cannot be Brownian one. But if you do these calculations, you'll get Brownian filtration.
Yeah, I'll show you a theorem later, and then we can discuss this result maybe in this context. Yeah. Right now, the only thing that I want to sort of draw attention to is that, again, sort of by plain vanilla calculation, if you take the k power of this matrix where the entries are now elements in this tensor space, it turns out that what you get here is exactly this signature object over all possible paths which connect node I with node j. Yeah, it's just check it yourself, but it's sort of an elementary calculation. Good, and then sort of what you try to do is sort of follow in complete analogy to the complete, classic diffusion on a graph case with this new object. So what you define is a new notion of the graph Laplacian, and then sort of like a nice exercise is proof, sort of a theorem of this form, that if you care about something like the expected value, where you compute the signature of this discrete random walk, conditioned on starting in the first node up to the end node, then this first fills again some sort of difference equation with this new hypo-elliptic Laplacian. And at the end of the day, you'd never have to solve this differential equation. Again, it boils down to sort of taking some k power of some new transition matrix identity minus this graph Laplacian. And that's, not so hard to prove, although it took us some time. But it's sort of like a nice, cute story. Yeah, the whole story is instead of, switching from your old matrix ring, you now switch to a matrix ring over tensors. Everything works out as before, yeah, and that's sort of like as nice as it can be. There is a story which I haven't told you yet. So far I've told you, well, for a given node I, how do I get a description of its local neighborhood? Well, this was exactly by diffusing out and then taking the average of these guys. But now what I have is for all of my n nodes, I have a good local description. And then we do something super simple. We just average over all these local descriptions to get a description of my graph. Yeah, so this is called pooling. Yeah, so that's exactly, we have these guys here, and then what we have is our feature map that I was after at the beginning. We plug in a labeled graph. And what we do is we average these local descriptions, which take values in this space of tensors. And one of the points of this whole previous slides is that you can do this by just linear algebra. Because obviously, if I jump from node I to node j, then what I've computed for node I already tells me a bit about node j, because node j random walks, they're just, concatenated, with the, well, I hope you know what I mean. Yeah, so anyway, so story up to here, we we get a better local description by remembering the history. We turn this into linear algebra, which makes it sort of computable. And then the question you ask, maybe that's an answer to it, or at least related. So what you want is sort of being able to distinguish between graphs, right? And what you can prove is if you give me two labeled graphs, G and G prime, and then you sort of run this random walk on labels, which means, sample uniform a starting point, take the average, blah, blah, blah. So we have these two feature maps, and these things are the same if and only if you can't distinguish the graphs between these two random walks. Yeah? So that's sort of maybe from a applied perspective what you care after. You want the characterization of the class of graphs that you can distinguish and describe with this methodology. Yeah? Good, and sort of what I think is good news in this thing is it connects very much to very classic theory. Yeah? So it's Rothschild-Stein lifting, Garot and Maillard and all those people, so really very classic objects in stochastic analysis. Then this trick of sort of taking your old matrices and plugging in tensors instead of vectors, this made it computable. Then you try it out, and then you see, well, okay, it was a nice idea. Sometimes it works a bit better than what people do in machine learning anyway. But it's not sort of like a game changer, and it comes with a huge overload of you have to learn what tensors, and it's always scary for people in this community. Good, and then the solution to this is to remember sort of really one of the big starting points of this whole deep learning revolution, which is that sort of often it's more efficient to go deep than to go wide. So what this means in this context is, what I just told you is a story where I give you a labeled graph, right? So I have the label of node 1, node 2, node 3, and then what I just discussed is, well, now there is a way to get a good local description of the local neighborhood of this first node. There's this node, and this node by remembering the history. And now all we could have done really is exchange the labels from RD, two labels in this tensor algebra, which incorporate sort of the local neighborhood structure. And the observation then is to say, well, okay, what we can do is we can now look at the functionals of this vector space, yeah, so this vector space of tensor series. And then really when you think about this from here to here, what we've just constructed is a transformation of a graph that's labeled in RD to another graph that's labeled in RD, right? Because we have these D functionals which turn any element of a vector space into the real numbers. Yeah, so we essentially, you can think about this, we run this through a smart nonlinearity, yeah? We transform the labels. And this is one step, and if you chain these steps after each other, it turns out that this is something very, very powerful, yeah? So you get a lot of expressivity with this. There is a catch with this, which is that, as I said, computation is a story. So first of all, storing this series of tensors is something that scales very badly. And then you again have to compute these linear functionals. And then there is a story coming sort of from this rough theory machine learning thing. And I just tell you the catch of the story. This is when sort of you have sort of an element of this space H, yeah, which is this series of tensors, right? So that's RD tensor 2, ... It turns out that if you restrict the attention to something called rank 1 functionals, yeah, so as for matrices, or a more general definition of the rank of a matrix is the rank of a general tensor, and the general tensor is of rank R if you can write this as the sum of R many of such elementary tensors. Yeah, and the idea is if you restrict yourself to rank 1 R tensors, then this thing here is really, really cheap to compute. And I'm not going to give you a proof of this. It's sort of like, if you know a bit about signatures, it's not hard to prove this. But then, of course, you run into this sort of like saying, okay, if I restrict myself here to rank 1 functionals, then yes, this thing is very, very cheap to compute. But then, by restricting, to a class of linear functionals, you restrict sort of the expressivity of this whole thing as well. But okay, I'm going to skip this as well. The idea is you can actually prove that if you repeat this D times, you again regain some expressivity. Yeah, so it's maybe more special remark for a rough audience, but so skip this. The idea is really we capture local information, local graph structure by these tensors. Then we care about linear functionals of these things. And somehow, for some reasons, these are very efficient to compute when you restrict yourself to rank 1 functionals. And by chaining this procedure, you can actually prove that you don't lose much by this restriction. Good. Anyway, back to what I wanted to do. At the end of the day, this is the object that we care about. We care about, this signature of this random walk on graphs. We take the expected value. Now we turn this, new label, which is valued in this vector space of tensors, again into a real number by computing a linear functional. And it turns out you don't have to pass this whole thing. The whole point here is that you can compute this quantity here sort of like recursively, and recursively is always something that you want when you are on a computer. And the big story here is, this quantity, when you sort of go through these observations, this is something that scales linearly in the number of edges, yeah? Because sort of the one theoretical answer to why do many of these graph learning things work in practice, even when you have sort of a 100,000 nodes or whatever, is that the graphs that you actually care about, you use in practice, they are sparsely connected. Yeah, and that's nice, yeah, because this is exactly you can't do better than something that scales linearly in the number of edges. Good, and then sort of the final thing I wanted to talk about is, the whole starting point here was to say, well, we start with a plain vanilla random walk and a plain vanilla Laplacian, graph Laplacian, but obviously what you would want to do is sort of like tailor-make the diffusion that you use to explore the graph based on the graph structure, yeah? And this falls into this whole notion of, could call this attention on graphs. You say, what I'm going to do is I somehow parameterize this adjacency matrix, and I learn this. Yeah, so somehow you learn the transition probabilities from the data itself, and I should say, you know, this works well in practice, but there are zero theoretical guarantees that we have for this. Anyway, so good. So at the end of the day, now we have a story that, you know, has some nice theory. It's computable. And then you say, okay, I'm going to test this out and benchmark it against everything that other people do. And this is sort of the stuff that you have to do when you sort of publish in these machine learning venues. And then sort of like, you know, sort of the stylized facts that you get when you know, go over a lot of data sets. Where this thing here really works well is to learn long-range dependencies. Yeah, so sort of, I don't have any sort of formal proof. You can sort of heuristically argue why this should be the case when you take the history into account. Then another thing that made a much bigger impact in graph learning is sort of this idea of transformers, which you all know from, you know, large language models and so on. And the whole bottleneck about transformers is that these things, they scale quadratically in the number of nodes, and proving things is much, much harder for transformers. And then a big topic in sort of like this sort of theoretical computer science or machine learning in this graph literature was sort of this idea of oversquashing. So what you have often is clusters of things that are fairly good connected, like, you know, a group of people, there's another group of people, and then there are a few edges in between them. And the problem that you run into when you run your diffusion is that you very seldom, you know, make the transition from one big cluster to the other one. And this runs under this oversquashing phenomenon, and again, somehow it turns out that this works very well there. Good. Open questions of this. Everybody in stochastic analysis, they will tell you, well, okay, once you start thinking about sort of these hypo-elliptic diffusions, this connects very closely to something called subriemann geometry. And what you want to do then is sort of use some of these tools of this sort of more geometric approach to maybe discuss some of these questions. We have done 0 on this. And then sort of a much more radical point of view, which I think some people are doing now, or this is at very early stages now in this sort of graph theory machine learning literature, is that you go back to Dirichlet's theory. So some of you might know sort of classic diffusions. There's sort of like this, again, I don't know, 1980s, 1990s approach where you do everything with Dirichlet forms, right? So you have your quadratic forms and so on. And this is especially powerful when you are sort of on complete discrete objects. And you can reframe all of this in Dirichlet theory, and I think there's still a lot of great potential there. Good. I think I finished early, yeah. So thanks a lot for your time. The paper is online, and you know, all references are in there. Good. Thanks.
Thank you very much. So plenty of time for questions. Expert in machine learning here. Very good questions. Right. Actually, I've got questions. Could you clarify the connection of hypo-elliptic diffusion with deep learning, for example?
In general, I don't know. Like so, you mean the last remark I made at the end with subriemann geometry?
You've got several layers, as you mentioned.
Yeah. So there's the general story now in machine learning, and there is a guy called Michael Bornstein. He's very active in this area. They sort of try to push further in this more abstract mathematical literature and see if this can answer questions that you have in machine learning and in graph theory. Yeah? And sort of this connection of lifting a Brownian motion to a Brownian motion with its iterated integrals. Turns out that it's, you know, actually doesn't fulfill this full, you know, space of tensors. It just lives in a subgroup and so on. And what you then can hope is that maybe, you know, some of these notions that you have from geometry, they give you some insights for things that you just encounter when you do experiments, like this oversquashing phenomenon. Yeah? So that's one thing that you care about. In general, if the story is, you know, how do hypo-elliptic diffusions feature in machine learning, what you would think maybe as a pure mathematician that it all boils down to sort of like making things smooth and sort of like how a pure mathematician thinks about sort of smoothing out distributions and so on. For me, that's not so much the interesting case there. Where it made a big impact is sort of the stuff maybe Terry talked about, which is this expected signature. So when you take, you know, a stochastic process, you look at its iterated integrals, you take the expectation of it, then it characterizes the law of the stochastic process. That's something that a lot of people use now in machine learning. And actually Nihao, who gave a talk, I think here as well, she then actually really used this hypo-elliptic Laplacian to write down the differential equation and solve it for stochastic processes. So yeah, there are many connections and it's still very much work in progress.
Okay, any other questions? Okay then, all people tired already, so thank you again. Thank you.